4 light-years away, orbiting the nearest star to our own sun, sits a small rocky planet that might have just cleared one of the biggest hurdles standing between empty rock and a genuinely habitable world. Scientists have found strong evidence that planets orbiting Proxima Centauri actually generate their own magnetic fields. Not maybe, not probably. Measured, statistically significant evidence, hiding in years of painstaking observations of the star itself. And if this holds up, it quietly rewrites how we think about almost every rocky planet discovered around small, violent stars just like this one, and there are a lot more of those stars out there than most people realize. Let's start with why Proxima Centauri matters so much in the first place. It is the closest star to our own sun, sitting about 4.2 light-years away. Close enough that it's practically our cosmic next-door neighbor by galactic standards, even though reaching it would still take our fastest spacecraft tens have actually built so far. It's part of a triple star system called Alpha Centauri, tucked in alongside 2 brighter companion stars, though Proxima itself sits noticeably further out from its 2 brighter companions, faint enough that you can't even spot it with the naked eye from Earth, despite technically being our nearest stellar neighbor, quietly orbiting that larger pair from a distance of roughly 1 trillion kilometers away. Proxima Centauri is a red dwarf, smaller, cooler, and dimmer than our sun, but these small stars are famous for one particularly nasty trait. They tend to be violently active, unleashing frequent powerful flares that blast enormous amounts of radiation directly at any planets orbiting close enough to stay warm. And Proxima Centauri does not disappoint on that front. This star rotates roughly once every 85 days, a fairly slow spin, yet it still manages to flare with startling frequency, with recent long-term observations showing the star was actively flaring for around 5% of all the time astronomers spent watching it. For a star this small, that's an aggressive, almost restless pace of activity, hurling bursts of radiation outward again and again, month after month, year after year, toward the small planets we now know are orbiting close by. Compare that to our own sun, which is calmer, larger, and far less prone to this kind of relentless outburst, and you start to get a sense of just how different and how much more hostile daily life would look on a planet circling a star like Proxima Centauri instead. Proxima Centauri hosts at least 2 confirmed planets. Proxima b, discovered back in 2016, orbits well within the star's habitable zone, the region where temperatures could theoretically allow liquid water to exist on a rocky surface, and it quickly became one of the most talked about exoplanets ever found, largely because of exactly how close it sits to Earth in cosmic terms. Then there's Proxima d, a smaller, closer in world confirmed a few years later, orbiting so tightly around its star that a full year there lasts barely 5 days, likely locked in a permanent embrace where the same side always faces the star, the same way our moon always shows Earth the same face. That tidal locking means one side of Proxima d likely bakes in permanent starlight while the other stays locked in permanent darkness, an alien kind of world with no real sunrise or sunset the way we understand them here on Earth. For years, one enormous question hung over both of these planets. Even if they sit in a zone warm enough for liquid water, does that actually mean anything if the planet has no way to protect itself from its star's constant radiation? Earth has an answer to that exact problem, a churning magnetic field generated deep inside our planet's molten core, wrapping around us like an invisible force field, deflecting most of the sun's dangerous particles before they ever reach the surface. Without that shield, many scientists believe our own atmosphere would have been gradually stripped away by solar wind long ago. The same fate many researchers suspect happened to Mars billions of years in the past, transforming what may have once been a wetter, more welcoming world into the thin, cold, dusty planet we see today. So the real question wasn't just whether Proxima's planets sit in the right temperature zone, it was whether they had anything like Earth's protective shield at all, or whether they were simply sitting exposed, absorbing flare after flare with absolutely nothing, standing between their surface and the stars. Fury, quietly losing whatever atmosphere they might have started out with, one violent burst at a time. This is exactly where the new findings come in. A team of astronomers spent an extended period conducting high-resolution optical observations of Proxima Centauri itself, carefully tracking exactly when the star's flares occurred relative to the orbits of its planets. What they found was striking. A significant number of the star's flares appeared to be phase-locked to the orbit of Proxima d, meaning the flares weren't happening randomly. They were timed, statistically, to specific points in that inner planet's orbit around the star, occurring far more often than random chance alone could explain, a pattern far too consistent and repeatable to simply be coincidence spread out across years of careful monitoring. That kind of time pattern is exactly what Scientists would expect to see if a planet's own magnetic field is actively interacting with its star's magnetic field as it orbits, essentially triggering flare activity through a direct physical magnetic connection between the two, similar in spirit to how some of Jupiter's moons interact with the giant planet's own powerful magnetosphere, funneling energy back and forth along invisible magnetic field lines connecting the two bodies as they move, relative to one another. Based on this interaction, researchers were able to estimate that Proxima d could carry a polar magnetic field somewhere in a wide range, roughly a handful of Gauss up toward several hundred Gauss, depending on exactly how large the planet turns out to be, and how its magnetic field lines up with the star's own field. This might be the first time scientists have ever managed to estimate a magnetic field, strength for a genuinely Earth-sized rocky planet orbiting another star, rather than simply assuming one exists, because Earth happens to have one, a meaningful shift from educated guesswork towards something grounded in actual measurable evidence, and the evidence didn't stop with the inner planet either. Researchers also found periodic changes in the intensity of the star's flare activity that lined up not just with Proxima d's orbit, but with signals tied to Proxima b as well, suggesting both known planets may be magnetically influencing their host star in their own distinct ways, rather than just one lone planet doing all the interacting. Why does any of this actually matter beyond simple curiosity? Because a planet's magnetic field might be one of the single most important and most overlooked ingredients in whether a rocky world can hold onto a breathable atmosphere long enough for life to have any real chance of developing. Without a magnetic shield, especially around a violently flaring star like Proxima Centauri, radiation and stellar wind can slowly strip away a planet's atmosphere over millions of years, turning what should be a warm, wet, habitable world into something closer to a bare, radiation-blasted rock, no matter how perfectly it sits inside that theoretical habitable zone. This is the exact problem. Many scientists suspect happened repeatedly across the galaxy, planets sitting in seemingly ideal orbital positions, only to end up stripped bare and lifeless because they simply lacked any internal mechanism to defend themselves. If Proxima b and Proxima d really do generate their own magnetic fields, that changes the entire conversation around their habitability. It means these worlds might have at least one crucial layer of protection against their host star's aggressive flaring, a fighting chance at holding onto an atmosphere rather than losing it entirely within the first few hundred million years of their existence, a survival window that might make all the difference between a dead rock and a genuinely living world. It doesn't guarantee either planet is actually habitable. Plenty of other factors still matter enormously, including atmospheric composition, surface temperature, and long-term stability, none of which scientists can fully confirm just yet from 4 light-years away with our current generation of instruments. But it removes one of the biggest reasons scientists had to write these planets off entirely, and that shift matters far beyond just these two worlds specifically. Red dwarf stars like Proxima Centauri are, by a huge margin, the most common type of star in our entire galaxy. And cooler, smaller stars like this one are exactly where astronomers expect to find the largest number of rocky, potentially habitable planets in the years ahead. If planets around active, flaring red dwarfs can realistically generate strong enough magnetic fields to protect themselves, that dramatically expands the number of worlds across the galaxy that might actually be worth taking seriously in the ongoing search for life beyond our own solar system, rather than automatically dismissing every planet orbiting a violent little star as hopelessly exposed and lifeless before ever taking a closer look. Since somewhere around 3 out of every 4 stars in the Milky Way are believed to be red dwarfs, just like Proxima Centauri. Even a modest shift in how we assess their planet's habitability could meaningfully expand the realistic list of worlds worth studying more closely in the years ahead. There's also something deeply practical about this discovery for scientists themselves. Detecting a magnetic field on a planet trillions of kilometers away is not something you can do with a simple photograph or basic brightness measurement. It requires incredibly precise, patient statistical detective work, watching a star's behavior shift in subtle repeating patterns over years of continuous observation, then carefully ruling out every other possible explanation, before confidently pointing to magnetic interaction as the actual cause. The fact that researchers managed to pull a usable magnetic field estimate out of that kind of indirect evidence on a rocky planet we will likely never visit directly is itself a genuinely impressive scientific achievement. The kind of quiet, methodical work that rarely makes headlines on its own, but ends up reshaping entire fields of study once enough of these small discoveries stack up together. Of course, none of this is fully settled science just yet. The magnetic field values researchers calculated for Proxima d span a fairly wide range, and confirming these results will likely require additional years of careful observation, along with independent studies. From other research teams working with different instruments and different methods entirely, science rarely moves in one single dramatic leap. It moves through exactly this kind of steady, careful accumulation of evidence, one flare, one orbit, one statistical pattern at a time, until a genuinely solid picture slowly comes into focus. The same slow, unglamorous process that has quietly built almost everything we currently understand about the universe beyond our own solar system. There's also a bigger, quieter implication buried in how this discovery was actually made. Astronomers didn't need to send a probe to Proxima Centauri, or even directly image its planets, to reach these conclusions. They pulled this entire result out of patient, ground-based observations of the star's own flickering behavior, carefully separating a genuine repeating pattern from ordinary stellar noise. That technique, watching for flare timing locked to a planet's orbit, could potentially be applied to plenty of other nearby star systems as well, meaning this same basic method might soon start revealing magnetic fields on other rocky exoplanets. Scientists previously had almost no way of investigating at all, simply by watching their host stars closely enough and long enough for the pattern to emerge. Upcoming instruments only make that possibility more exciting. Next-generation telescopes currently being built or recently brought online are specifically designed to study small, rocky planets around nearby stars in far greater detail than anything available today, examining their atmospheres, their surface conditions, and potentially confirming magnetic activity through several independent methods at once, rather than relying on a single technique alone. If Proxima Centauri's planets really do turn out to have working magnetic fields, they instantly become one of the highest priority targets for exactly this kind of deeper, more detailed follow-up investigation, precisely because they sit so close to us compared to almost every other exoplanet system currently known, and proximity, when you're trying to study something as faint and distant as a planet's magnetic field, ends up mattering enormously. But step back and look at the bigger picture here, and it's hard not to feel the weight of what this actually represents. The nearest star system to our own sun appears to host at least one rocky planet with its own working magnetic field, sitting right there in the habitable zone, 4 light years from where you're sitting right now. We are not talking about a planet on the other side of the galaxy, impossibly distant and forever out of reach. We are talking about our closest cosmic neighbor, a system future telescopes and, eventually, future missions may actually be able to study up close in ways scientists could only dream about just a few decades ago, when Proxima Centauri was still just a faint, unremarkable dot buried in a crowded southern sky. If discoveries like this genuinely fascinate you, make sure to like this video and subscribe, so you catch the next update the moment new research on Proxima Centauri comes in. Do you think Proxima b could actually turn out to be habitable, magnetic field and all? Or is a flaring star like this simply too hostile, no matter how well protected a planet might be? Drop your take in the comments, because this is exactly the kind of debate that's going to keep evolving as more data rolls in over the next few years. And honestly, a working magnetic field on our nearest planetary neighbor is the kind of detail that makes the whole search for life outside our solar system feel just a little bit closer than it did last week.